Hello everyone, welcome again. So today's lesson will be on the energy module of Year 11 Chemistry. And in today's series, or in today's lesson, we're going to look at classifying combustion. And the reason why we're looking at combustion in terms of energy is because combustion is how we generally get energy out of a chemical. So if we had a chemical with lots of chemical energy, we might want to convert that into something else. And so we generally use combustion to get that energy in the chemical into another form that we can use for other purposes. Okay? So for instance, if we want to turn chemical energy from petrol into motive energy in your car, we will use combustion to do that. Okay? So that's why we're looking at it in the energy topic. Okay? So today's lesson will be on classifying combustion. So we are going to classify combustion into different categories so that we can sort of differentiate between one type of combustion for one application compared to other types of combustion for other applications. Okay. So combustion reactions are an extremely important industrial process. Basically, any sort of power generation, with the exception of most of the renewable power generations, are combustion of some description. Coal, natural gas, oil if you have that kind of money available, I suppose. If you want to generate electricity, you'd use combustion. In your car, you use combustion to move your car from place to place. So you can see obviously in trucks and planes, they also use combustion. So you can see that combustion reactions are pretty much everywhere already. And the reason why they've become so big is because it's an easy way to get energy from place to place, because chemicals can store a lot of energy for us. Okay. All combustion reactions involve some kind of fuel and an oxidant. Now the fuel is usually a hydrocarbon, but it could be lots of other things. So generally something that has a lot of stored chemical energy is a good way to describe the fuel. And an oxidant is something that causes the fuel to oxidize. And so it is essentially something that causes the reaction. Usually it's oxygen, as in the oxygen in the air, but it could be other things like nitrates and other chemicals. So it's not always oxygen, but most of the time it is for combustion reactions that we deal with. Okay, so the oxidant is usually oxygen, but it doesn't have to be. So some more things about combustion. They're all exothermic, so they release energy in the form of heat and light to the environment, and so they release heat and light to the environment. Okay, so they're all generally exothermic. You don't really see any combustion reactions that are endothermic because that doesn't really make sense. Okay. So factors affecting combustion. So you can see in these two pictures, you've got combustion happening, but they look very different. So this is sort of like the combustion you see if you have coals for a barbecue. For those who but for those who use coal in your barbecue. And this sort of looks more like the combustion that you see in your stove if you have a gas stove. So this is like a lab burner. So a lot of lab tests are done with these simple burners. And you can see the flame structure is very different to here. And so we need to figure out reasons why. Okay. So the actual rate of combustion depends on lots of different factors. So the different factors include the nature of the reactants, so what the reactants actually are, how much surface area is exposed. So a droplet of fuel has much more surface area than this big coal. Okay, much more surface area per volume than this big lump of coal. So that's a big factor. For the biology kids, that should be very familiar to you, the surface area to volume ratio. The concentration and pressure of the reactants. So if you put it under pressure, or how much of a particular reactant you have, affects the combustion as well. Temperature, this is a big one, temperature of the system. So preheating the air and things like that, that can be an issue for the combustion reaction as well. And of course the use of catalysts. So if we use a catalyst, usually they go faster, they react much better. And if we don't, they tend to go slower. Okay. So based on how fast these reactions occur, we can split combustion into three categories: slow, spontaneous, and explosive. Okay, so we'll look at each one in depth in a second, but we'll just say for now that we split combustion into three categories: the slow, spontaneous, and explosive. Okay, so we'll look at slow combustion first. So some combustion reactions can occur very slowly. So here you have wood sort of just smoldering. It's still combustion, but it's just happening very, very, very slowly. So if you've ever been to a bonfire or something like that, you'll see this, and it's just slow combustion. Now the reason why we get slow combustion is usually because the fuel particles aren't as mobile as a gas. They're not as mobile, maybe because they're a solid or something. So they can't move as freely as a gas can, so you get much slower reactions. Now because they're not as mobile, there's less number of collisions that can occur, so obviously there's less reactions happening. Another way of looking at it is that fuels with low surface area to volume can also combust slowly because the oxidant can't actually access the fuel. So if you've got a lump of fuel like this, okay, this is your lump of fuel, and you've got oxygen all around. Okay, you've got all this oxygen around. They can only sort of access the top layer, right? So just this section on the outside. But they can't get into the middle bit, so the reaction rate is obviously slower because they don't have access to all of the molecules in the fuel. They only have access to the outer surface. Okay? So if you have low mobility fuel or fuel with very low surface area, you get very slow combustion. Okay? So examples of slow combustion include coal burning. So when I say coal burning, I mean like lumps of coal, not the type of coal burning that you see in a power plant, but I'm talking like that barbecue coal that I showed you before, and wood burning like this. So wood burning is an example of very slow combustion. Okay, there are of course other examples, but these are the two most common ones that you'll see. Obviously coal you see in your barbecue, and wood at a fireplace or in a bonfire. Okay. So in general, we can speed up these slow combustion reactions by increasing the available surface area. So how could we do that? Well, we could just grind up the coal into a dust or powder, and then we've got all this surface area, and then we can burn it very quickly. Or we can chip up the wood, so throw it in a wood chipper and get like little chips of wood, and that will burn much faster than the lump of wood. Okay? So in general, we can increase the surface area, and that will increase the reaction rate. So then now that we've talked about slow combustion, we're going to look at spontaneous combustion. So basically spontaneous combustion is just combustion that occurs at room temperature with no clear ignition source. Okay? So basically there must be no spark or other additional energy input to describe a reaction as spontaneous. Okay, so what that means is, for instance, petrol I can light on fire at room temperature, right? I can get a spark and light this petrol on fire. But that is adding extra energy to the reaction, that spark. But a spontaneous combustion reaction will just instantly ignite at room temperature. Okay, so you put the fuel in air at normal temperature, and without any additional input, it will just catch on fire. Okay. So that's the difference between, say, petrol combustion and a spontaneous combustion. Okay, so there's no spark or ignition source in spontaneous combustions. It's just fuel in air, and all of a sudden it catches on fire. Now, of course, very few substances react in this way. Okay, otherwise you'd see fires just popping up randomly all the time. So there's very few substances that would actually do this. For many reasons. But one example is white phosphorus. So here's an example of white phosphorus just burning. It's an allotrope of phosphorus. So what that means is it's phosphorus just bonded in a different shape to the normal phosphorus. So that's what white phosphorus is. It's just a type of phosphorus, and the structure is different to the phosphorus that we see in everyday life. So what happens is you've got to store it in water, because when it comes into contact with air, it burns with a yellow flame to form tetraphosphorus decaoxide. So here it is. So tetraphosphorus decaoxide, and it forms a white powder. White phosphorus is actually quite a nasty chemical, and a lot of military research is going into using it as a napalm or some kind of incendiary weapon. It's quite a cruel chemical to use as a weapon, so that's not a very good thing, but it's an example of how spontaneous combustion occurs. So when it comes into contact with oxygen, this reaction happens, and you get this white powder, which is tetraphosphorus decaoxide. Okay, so that's an example of spontaneous combustion. Very, very, very few chemicals will actually do this. This is just one of the minority. Okay, so spontaneous combustion is not common. Now, one type of combustion that is more common is the explosive combustion. So here you have like basically it's just a stunt, frame by frame of an explosion for a movie or a special effects scene, and it's pretty typical. You've all seen explosions before. Hollywood movies like to use them all the time. But an explosive combustion is a rapid and contained heat production in combustion reaction. So with a fire, when you have a fire, there's my flame, okay? The heat can just go wherever it wants. It's not contained in any way. It's contained in the, sort of the bounds of the universe, but it's not contained, within the size of the flame. Okay, so the heat just goes wherever it wants. Now with an explosion, what happens is you actually contain the flame somehow such that the heat is trapped in our little container. So the heat kind of bounces around our container. Because it's trapped in the container, the temperature will then suddenly rise, right? Because all of the heat is being stored in the container, so the gases start to heat up and the temperature starts to go up. Then the pressure starts to go up, and then that's when an explosion happens, okay? But we'll talk about that in a sec. But that's what we mean by a contained heat production. The heat gets stuck in a small area around the flame, okay? Now the reaction rate increases very rapidly because the heat is confined, and then the temperature goes up. So because the heat is confined, the temperature increases, which increases the rate of reaction. So this results in a rapid increase in temperature and pressure. So the pressure goes up very rapidly. And explosions are the rapid expansion of the product gas. So when the pressure goes up to high enough that it can actually rupture the container, then that's when an explosion happens. Okay? So the gases suddenly rupture the container, they push outwards, and then it goes everywhere. And then that's what's happening in this picture here. So the gas is expanding, and then that's what an explosion is. Okay? So basically when you contain the heat release, you get this sort of feedback loop. So you contain the heat release, the temperature goes up. The temperature goes up, the reaction rate goes up. The reaction rate goes up, the heat release goes up. And then it just keeps going around in circles and circles until you get to the point where it explodes. Okay? So basically that's how it works. When you contain it, everything goes upwards, including the reaction rate. So you get more heat. More heat means even bigger temperatures. Even bigger temperatures mean even bigger pressure. And then finally explosion. Okay? So a rocket engine is an example of an explosion. There you go, there it is. And if you've ever seen a rocket launch, you'll see why it looks like an explosion, or why it's called an explosion. But they basically allow liquid hydrogen and liquid oxygen to combust explosively in the engine. And then large volumes of water are expelled at the bottom. And that pushes the rocket upwards, okay? So that's what an explosive combustion is. Okay, so that concludes today's lesson on classifying combustion. So we looked at what are the three types of combustion and what is combustion in general. So we'll move on to the question segment now, and then hopefully that will give you more insight to the applications of combustion and how it and how we classify it. So question 1, identify an example of slow combustion. So that we gave you examples in the first couple of slides on slow combustion. So one that we haven't showed you is the oxidation of iron. So when iron rusts, it's actually a very, very slow form of combustion. But other examples that you could have used were coal burning or wood burning. Spontaneous combustion. Another one that we didn't show you was the combustion of a wet haystack. This may sound like a really strange one, but basically when you have a haystack, if you, for instance, work on a farm, if it's wet, it tends to absorb energy, right? And the haystack will actually store that energy in the middle. So when the sun shines on it, so here's our happy sun. When the sun shines on it, it heats up, okay? Then when it's nighttime, you think it would cool down, but it actually stores the heat inside because it acts as a fairly good insulator, okay? And then once it's stored up enough heat, it can actually catch on fire. So there have been cases of haystacks just randomly lighting on fire simply because they've just been sitting out in the sunlight for too long. Okay, so in general, this doesn't happen very frequently, but it is an example of a spontaneous combustion because you don't have to light it on fire; it just catches on fire sometimes. Okay, and explosive combustion. So it's the combustion of hydrogen and oxygen. In the case of the rocket engine, that's what it would be. Okay. So wood combustion is typically seen in many households, so lots of people still use wood-fired fireplaces and things like that. Explain how wood can combust if each wood molecule needs to collide with O2 molecules in order to burn. So this, when my chemistry teacher, when I was doing HSC chemistry, explained that combustion needs to occur, all combustion reactions have to be in gas phase. I always was curious as to why wood still burned, because wood is obviously a solid, not a gas. Okay, so what's actually happening? Well, wood particles are far too large and too tightly bound to one another to react with oxygen. Okay, so the wood molecules are enormous; they're huge particles, and obviously they're not going to, become gaseous and burn. Okay, so they're too big and too tightly bound to each other. However, when we apply heat to them, the wood particles actually break down into smaller gaseous particles, which is called thermal decomposition. It's actually also called pyrolysis. So when you heat wood, the central part of the wood has no oxygen available to it. So it actually breaks down into smaller molecules, and so those molecules are actually flammable. Okay? So these gaseous particles escape through fissures in the wood to interact with oxygen. Okay? So the molecules actually escape through cracks in the wood, and then that's where they burn. Okay? So if you ever looked at a piece of wood that's burning, you'll see there's always a crack. Like the wood would be here, there's always a crack, and the flame will be coming out of the crack. And the reason why that happens is because this crack is where all the gases are coming out of. That's where they're sort of leaking out of, and that's why the flame is there rather than anywhere else. Okay? Explain a situation in which controlled explosions are utilized for industrial applications. Okay? There could be lots of examples of this. Dynamiting in mining operations, when you use dynamite to blow things up, or to move rock from one place to another, is one example. But here's a more close to home version for you guys. So the operation of an internal combustion engine is essentially a repeated series of controlled explosions. This sounds like a really dangerous thing, but your car is just running on little tiny explosions that we're controlling to use for our own purposes. So when fuel is burned, there's a rapid increase in pressure in the cylinder. So you've got your car has a cylinder and a piston. So when fuel burns, it's like a little explosion, which creates a really big pressure rise in your cylinder. Now this pressure rise forces the piston downwards, or pushes the piston, which causes the motion of the engine. Okay, so that's one application of an explosion that's pretty close to home, your car. So it sounds really dangerous, but we've had years and years to develop ways to safely do this. But it is an explosion still. Okay. Explain why spontaneous reactions are not common among hydrocarbons. So we're talking about most hydrocarbons here. There are very few examples where I would think spontaneous combustions actually happen. But why are they so rare in hydrocarbons? Well, hydrocarbons in general have many bonds per molecule. So if you think about even the smallest one, methane, each molecule has 4 bonds that you have to break. So in order for these molecules to react, there needs to be significant input of energy to break all the bonds. So you need to put in enough energy to break each of the bonds. Okay? Now often the ambient temperature doesn't provide enough energy for these hydrocarbons to react because it can't break all of those bonds. So that's why hydrocarbons rarely undergo spontaneous combustion. It's very, very unlikely. And question 5. Describe the energy changes that occur during combustion reactions. Well, in general, the chemical energy within the fuel is converted into heat and light. And then this heat can be utilized for other purposes, can be turned into mechanical work, which then gets converted into electricity, could be converted into other forms of energy depending on your application. So that's basically the energy changes in a combustion reaction. So that concludes today's lesson on classifying combustion reactions. We looked at what are the 3 major types of combustion reactions: slow, spontaneous, and explosive. And we looked at combustion reactions in general. So next lesson we're going to look at reaction rates and how to increase or decrease reaction rates in a first-hand investigation. So I look forward to seeing you at our next lesson.